So suppose there is a rod and I'm constraining at this location and pulling it in 1000 newtons in this direction. How to calculate the stresses using FEA? I'm using HyperMesh as a preprocessor and Hyperview as a postprocessor and MSC Nastran as a solver. Hi, let me create a cylinder first for this analysis. So diameter of this cylinder is 16 mm. That means I need to keep the radius as 8 mm, and height of this cylinder will be 1000 mm. So I will put radius as 8 and height will be 1000. So done. This cylinder creation is done. Now I can go to here map solids, and it is easily a mappable solid. So I will just click on this mesh, click on mesh. So if you see here, there are only 3D elements and mesh has been created. So I'll just exit this panel. Now I can just hide this one, and now my 3D elements are created. So I need to fix one end and I need to apply the load at the other end. So for fixing this, I can just go on here to the model and I can create one RB2 here. So I'll go on and calculate the independent node, and for dependent nodes I can just choose this face and apply OK, and all degrees of freedom I want as dependent degrees of freedom. OK, it is already created. Now I need to create here one RB2 mode to apply the load. So I can just go on here and do the same thing, create one RB2 here. Done. Close. Now my solid elements and RB2 are in the same collector. I don't want that, so I will create one more collector here and just organize my element to the RB2 collector. Just click on yes. That's it. So I'll just change this color for better visibility. Oh, sorry. Yeah. So I have applied the auto color. Now we need to define some load collectors to properly constrain our model. So firstly, I'll just go on here and apply the load collector here, and I will type it as uh, fix, any name you can give, and then I can just go on here and go to analyze and just go on this constraint options and select this node, and this node I want to constrain it in all direction, all DOF. So I will just choose this node and press OK, create. That's it. uh, my SPC has been, my constraint has been created. So you can see here, uh, yeah, so you can see in the load collector it is written 1 2 3 4 5 6. That means all 6 degrees of freedom you can constrain. And then I need to apply the load here, so I will create one more collector here, and I will just apply the loads here. So loads here, and just this node I need to apply the load, and it will ask me the magnitude of this load. I need the constant. uh, there are several options here. You can just go to constant vector or constants components. So I will just go on constant components, and you can see here I need to apply this load in the negative of z direction. So I'll just go on here and go minus 1000 and just click OK. So this load has been applied here. So you can see this one. This is my force and this is my constraint. Okay. Now I need to define. I have just created the elements, but I need to define some material also to this element. So for material, I need to define the steel. So before defining the steel property, this is in mm's and this is in force is in newtons. But the MSC Nastran is a unitless solver. That means we need to define the units in a consistent manner. So the Nastran, MSC Nastran, and almost many FE solvers are unitless, which means that whatever we are defining the model, the other units will be depends on those units on which model is defined. So in this scenario, we have defined the forces. Force in Newton, length is in mm, our geometry is in mm, and time will mostly be in seconds for almost all mechanical analysis. So that means that the area will be in mm square and the volume we need to define in mm cube, which also means that the stress, which is also known, which is equivalent to force by area, will be Newton per mm square, which is also equivalent to MPa. So if you got from these units, you got suppose 5 units of stress, which is nothing but 5 Newton per mm square of stress or 5 MPa. Then again, accelerations, if it is acceleration we need to define or we are outputting the acceleration, it will always be in mm per second square. Then we also know that the force is equal to the mass times of acceleration, which means that if the force 1 Newton of force is nothing but 1 kg into 1 meter per second square of uh, and 1 meter is nothing but the 1000 of mm. So 1 Newton is equal to the 1000 kg into mm per second square, which is nothing but the again the mass times acceleration, which means that the mass we need to define in thousands. So again, 1000 is nothing but 1 tons. So again, the mass we need to define in tons, which means that density is nothing but mass per unit volume. So we need to define our density in tons per mm cube. So the reason of this calculation is like we need to define our density and Young's modulus in which unit. So Young's modulus is again the units is in uh, Young's modulus units are in the same units of stress. So again coming back to the what we need to input in hypermesh or in nastran. So density of steel is we everybody knows is 7,900 kg per meter cube. So which is nothing but in tons we need to define the density in tons per mm cube. So it comes out to be 7.9 10 raised power minus 9. So the software doesn't understand 10 raised power minus 9, it understands e power minus 9. So, and again, Young's modulus is again 210 GPa for most steels, so which comes out to be 210 E3 Newton per mm square or MPa. As we already know that 1 MPa is 1 Newton per mm square. So this way we need to put it E mu and rho. So rho is density, mu is Poisson's ratio, and E is Young's modulus for this analysis in MAT1 card. And Poisson's ratio is, we already know it is unitless, so it will be zero point 0.3 in for steel in all unit systems. So if you still find difficulty, you can go to this below link, and it is the most consistent unit is already set here, and you can go on here and uh, convert your units to your consistent units of FEA. Suppose if I want to, uh, I know the mass of my system in kgs, I will put here, suppose my mass is 10 kg, it will give me in my consistent units of FEA 10, which is 0.001, which is in tons. Okay, yeah. And suppose if I want to use Newton, if I want to input my one misses, sorry, if I want to use the Young's modulus, which is in GPA, I'll put here suppose 210 GPA. So it will give me, yeah, so it will give me in MPa, which I can use in my Young's modulus. So this is how you can convert the units, and other things are also specified here. So you can use it in your FE model if you find difficulty while converting. So based on our calculations, below are the materials we will define it here. Just go to create and go to your material, and then there is a mat1 card, which means that this is a linear structural material. So E is the Young's modulus, you can define it 210 E3, that means 210 10 power 3, 10 raised to power 3. Now G we don't need to define, nu is nothing but Young's modulus, so we can define it as 0.3, and rho is whatever we have calculated, we can define it here, that is 7.9, 10 raised power minus 9, which is E minus 9 here, and other things we don't even define it here because this is a linear elastic, and this settings are enough for it. Now this I can just, this is my material 1, this I can rename it if I want, that is steel. Okay, now we have defined it, we have just created the material card here, but we need to assign the material in this elements, and we can't directly assign the material in the elements, we need to go via, we need to define via property. So property, this is a solid element, which means this is a 3D elements, so that means we need to define it as a p solid, and then p solid, other things you can keep it as default, and just material you can define it as this steel material, you can select it here. Now this property contains this material, but this component doesn't contains this property, so again go back to this component and just define this property. That's it. Now if you are not sure whether you have defined it, just go on here and click one element, double click one element, and you will have this property, uh, and you can again just go on here and edit this, and you it will contain steel. Okay, so once we have defined the property, now uh, we just need to create the load step. So this is the first load step here. So this analysis type is generic. You can keep as it is, or you can just go on here and click linear static. Then SPC. SPC is single point constraint, which means whatever the constraint you need to define, you need to put it in SPC. So you can go on here and click on this one. Okay. The load means whatever the force you are defining, you need to keep it as load. You just click this and press OK. Other things are fine. Now whatever the output you need, you can put it here, or you can put it in global collector, global output collector. So I will put it in global output collector. And one more thing is subcase. So subcase name you can change it. So I'm changing load 1000 Newton. That's it. Now there are many more things here. So now there is one more thing here is you need to define the case control card and param card. So param card is there are some additional settings in MSC Nastran which you need to define. So there is post card. So post I will define it as -1, which means it will write the OP2 file which can be opened with Hyperview. If you don't define it, it default it will be 0. That means it will create the XDV file, which is a old format file. Other things are fine, and then I will just create one more output card, which is case control card. So this is global case control card, and I will just output some of the properties here, some of the output like stresses and all. So this analysis type is statics. Sorry, this is a global case control card, which means I need to define it as statics here. And then I just need one more card here, which is output card, which is global output card. So I need here displacement and sorting. We will discuss it later. Format is I want it in plot format, which means that it will plot it in OP2 format. And form, you can skip this form for now. And set ID, I just need it in all the elements. And I also need load here. Again, I need it in plot format. And then SPC forces, I also need it. Again, I need it in plot format. And I need stress also. Again, I need it in plot format. That's it. So this is done. And now I will just export it. Just go to here, export, and explode solver deck Newton. So there are various things you can do. Just go here and press all. Format will be standard. There are three formats basically. Standard format is short format, which is the most usual format here, and long format we don't it is not mostly recommended, and free format is easy to understand. So currently we will use here standard format, and then you can just go on here and just export this. You can even switch off the comments if you want, but it will be little bit more difficult to read. Then we will just go on here and export this solver tag. So once this is done, you can go on here and go to the folders where we have exported this. So you can go here and see this one. So we can go on here and just go to here Nastran and just try to solve this, whether we are able to solve it or not. So basically we it will throw one error. Go on here and see there is some job is terminated due to lack of sol card. So just go on here again and create one sol card here. So this is a statics, just click on statics and that's it. And you might be thinking why everywhere we are placing statics. So if you don't want it, like just go here and press generic. Uh, 1 second. Yeah, let it be. So we will just go on again and export this deck again. And I will delete these files and just try to solve it again. So after this OP2 is been generated, always first check the log file here. So log file contains almost many important information. So you can see here it has acquired the licenses, finite element model generated. This is the degrees of freedom of this model, and application load has been applied, and then linear static solution is also completed here. Secondly, we can check here the F06 file, F06 file, and then we can go at the very last and check the fatal, whether there shouldn't be any fatal keyword. Here also you can select this load table, and epsilon and external work is there. We will see it what it is and how is it useful. And then we can just go on here, just click on one more window here and just maximize this. Go to Hyperview here. So we can go on here and click the input output file. So input file is again the BDF, and the output file is OP2. Even we can just open the OP2, it should contain our results. So just click on here in this fashion and switch on the mesh, and then first thing should be animate this. So we have applied some load, but we can't even see anything. Yeah, the loads is very small, so we will just scale our deformation, maybe more. So you can see here we have applied the load in this direction, negative Z. So it is extending our bar, and this side we have fixed it. Now we can just go on here and again set the deformation to 1, and then we can just go on here and check our displacement. So you can see here is point 0, uh, it is 0.0242 in this end, and here it is almost 0. And the displacement should only be in Z direction. So we can see it should be in primarily Z direction. Yes. So you can see here is this side it is negative Z, so it is calling it as negative. So it should be overall magnitude should be here, and x and y should be equal to 0 or nearly 0. So it is e power minus 5. So this is nearly 0. Okay. Now once this is clear, we can go to here applied force. So applied force should be in this direction, should be in the rigid only, and you can see here if I am able to annotate I will show you. Just go to here, measure, contour, and just click on this node. Sorry, just click on this node. 1 second. I need to hide this to properly click on this node. Yeah, so we have applied 1000 and we are getting it 1000 in O load. So this is the meaning of O load, means whatever you are applying in FE model, you should get in the O load here in OP2 format. It should be in Z direction only. Yeah. So we have applied in negative Z and we are getting in negative Z only. Okay. So now this applied force concept is cleared. Applied moment should be 0 everywhere, just like X and Y direction. Rotation should also be 0. Now what is SPC force and moment? SPC force is nothing but whatever the reaction force we should get at our constrained location. So we are applying 1000 here. We should get the reaction force as 1000 here. So this is one of the checks you should always do in static problems, whether your constrained locations contains whether there is force balance and moment balance in your model or not. So I should get here the same. Okay, again I click some other node. I should just hide it this one and just click on here. So it is 1000 again, and just to make sure, just put. So this means I'm applying the force in negative Z and I'm getting the SPC force in positive Z at the other node, which is fine and acceptable under statics. Now I will just see the stresses. So I will just go on here and See this stresses. Just for time being, we will forget about what is this averaging method, and we will just go on here advanced method, and we will discuss this what is corner data and what is averaging in some other video. For time being, we'll just go on here and click on apply. So this is our one misses stresses, and this should be uniform all over here. So I'll just go on here and click on this any node here. I should get the same one misses stress, and I should also get the uh, sigma zz as same as 5.011, approximately same. So I just go on here and click on sigma zz. So it is 5.01, which is same. So this means our analysis is correct only. Now again get back to here. So in order to measure this area, I need to first calculate this, extracts the faces of this element, as it is a 3D element. Now the faces will become 2D element, and now I will go to here, this measure option, and go on calculate, and instead of components I will choose elements and just select the face elements here. So only this 2D elements has been selected. Now I will compute it. So area is 199.11 mm square. So yeah, so now so area is 199.11 mm square. Now, so stress we have applied is force by area, and we have applied 1000 Newton. So 1000 divided by 199.11. So which comes out to be 5.02 Newton per mm square, which is also same equal to 5.02 MPa. So in FEA, as you all know, we are getting 5.011, which is quite similar to whatever we have calculated via our basic solid mechanics hand calculation. Now there are few points which might be interesting to you. Uh, like we can discuss it here now itself. So you might be thinking like, let me just switch it on first. Okay. So you can see here we have constrained it via this node using this rigid element. So you can, without rigid element also, you can constrain all these face nodes also. That is one possibility. And even 456 doesn't means anything because this solid element contains 3 degrees of freedom each node. So even if I constrain 1, 2, 3, that's fine also. Second thing is, instead of 1000 Newton applying at the rigid node, I can directly delete this rigid, and I can apply this 1000 Newton, 1000 divided by the number of nodes in this phase, and I can apply this 1000 divided by n to each of this node. My result will be same. So this is the most basic linear static MSC Nastran deck we have seen. So just try it out, and thank you. Have a great day. Bye.